Chapter 4, Isomers. Isomers are chemicals that have the same molecular formula, but they have different structures. Those different structures can appear two different ways. We can have constitutional isomers, so something like if we had propanol, this is one propanol, or if we had two propanol. What we have here are constitutional isomers. They differ in the way that their atoms are connected. Stereoisomers are the ones we're going to focus on the most here in this chapter. Now, stereoisomers differ in the way that their atoms are arranged in space. Now, we can look at cis-trans. So if we had a dichloroethene, this would be the trans, and then the cis is when the chlorines are on the same side. And then we have these isomers that contain asymmetric centers. This is the particular group of isomers that we'll spend the most time on. But it's important to get used to some of these keywords and phrases. So when we have constitutional isomers, here's ethanol, dimethyl ether. Again, they have the same chemical formula, but the atoms are arranged differently. But then we have our stereoisomers. Cis-Trans Isomers, they come about because of restricted rotation. So we have this cis compound that's both on the same side of the ring, or we have trans on top of the ring and below the ring. Not all alkenes are going to have cis and trans isomers, and that's important to note, because if one of your carbons has two of the same substituent, you will not have cis and trans. Now, it's important not to mix up conformation and configuration. And this is actually the best explanation of conformation and configuration that I've seen. If you have a dog standing on all four of his paws, and then you take that same dog and he only stands on one paw, you still have the same dog. He's just in a different situation, kind of like a person sitting versus a person standing. However, if you have a dog in this configuration, and then you take it and switch it so that the leg is in the tail's place and the tail is in the leg place, then what you have here is a different configuration. These are what we're looking for here. Cis-trans isomers have different configurations. They've put the tail in a different spot. We're building up towards more talk about stereoisomers because we're talking stereochemistry, the arrangement of atoms in space. But in order to talk about stereochemistry, we need to talk about the asymmetry and the chirality. Now, a chiral object is something like your hands. Your right hand and your left hand are mirror images of one another, but they are non-superimposable. You can't take this image of the right hand and put it over top of the image of the left hand and have them be superimposable. Similarly with ears, your right ear and your left ear may look an awful lot alike, but you cannot take this image and simply move it on top of the other one and have it match. They're mirror images, but they are non-superimposable. In contrast, we have achiral objects, something like this chair. This chair has a line of symmetry in it, and therefore its mirror image is superimposable upon itself. A fork or a glass of milk is similar in that capacity. So specifically when we're talking about chiral molecules, we're talking about a molecule that has an asymmetric center. Now this asymmetric center is actually pretty easy to pick out. An asymmetric center is going to have four different groups or atoms attached to it. So for example, with 2-bromobutane, the asymmetric center is indicated by this asterisk. So we have a methyl group attached to it, a bromine group, a hydrogen, and an ethyl. So we have four different groups attached to this carbon. Now you can pick asymmetric centers out fairly readily when you know what to look for. Here we have a propyl group. Here's our alcohol. We have this chain, a butyl group, and then our hydrogen. Similarly over here, we have 4 different groups. So when you're looking for chiral and achiral molecules, you're looking for its mirror image, and you're looking to see if it's superimposable or not. So in an enantiomer pair are 2 chiral molecules with non-superimposable mirror images. An achiral molecule, however, has its mirror image. See this, there are 2 hydrogens here, and its mirror image is actually the identical molecule. In your lab, you'll practice some of these with your molecular model kit. In order to determine if you have a stereocenter as well as an asymmetric center, you need to look at your asymmetric center. Now, all asymmetric atoms, that is an atom that has 4 different groups attached to it, will be stereocenters. But not all stereocenters are asymmetric atoms. For example, if you have a double bond, that double bond, if we flipped these 2 atoms here, then we switch from a cis to a trans, and that's a different isomer. Therefore, these are stereocenters. Now these are stereocenters as well because if we flip the position of, say, this chlorine and the hydrogen that comes to the back, comes to the rear, then we've changed from a cis to a trans. So these are stereocenters, but they are not asymmetric centers. There are 2 different ways to draw enantiomers. You can use the perspective formula, which involves the dashes and wedges. Dashes here, wedges here. Wedges indicate that that particular bond and compound is coming out towards you, and the dashes indicate that it is going behind the plane of the paper or screen, as it were. These straight lines here indicate that it is in plane with the paper or the screen. So when you make these molecules, think of the dash as coming out towards you, or the wedge coming out towards you and the dash receding behind. Now we also have Fisher projections, and in the Fisher projections, the asymmetric center is in the center of a crosshairs. So these are Fisher projections of these perspective formulas, and as you can see, in the plane of the paper goes horizontal, and the group that gets the dashes goes to the north position, the top, and the group that gets the wedge goes to the bottom position. In order to name enantiomers, we need to assign a ranking priority to each of the 4 groups around the asymmetric center. Now, in order to rank those groups, we need to figure out which atom has the highest atomic number. The atom with the highest atomic number will be assigned a priority of 1. Now, the default to that is hydrogen will always be assigned a 4 because it is the atom with the lowest atomic number. So we have our top and we have our bottom. So now what we need to do is figure out how to rank these groups in between. Now, because this carbon is attached to a carbon here and it's attached to a carbon here, there's a tie. So we need to look to the next atom it is attached to. This carbon is bonded to another carbon. So we can see this as a C-C bond, whereas this is just a C-H bond. This carbon is only attached to hydrogens. So the ranking goes bromine is number 1 because it has the highest atomic number. Number 2 is the ethyl group because we have 2 carbons bonded to one another. Number 3 is the methyl group. And number 4 is the hydrogen. Now after we assign those priorities, and you can see that these are mirror images of one another, and we've assigned the priorities and they go in opposite directions. Now what we're doing is we're going to figure out how to name it based on these priorities. We're assigning these priorities in order to name our enantiomers. So we're going to first name it with our root. We have a carbon chain of 4, which gives me butane. I have a bromo here, so I have a bromobutane, and it is on carbon number 2. This is carbon 1, and this is carbon 2. So we have 2-bromobutane. Now this is the part we're adding. We are adding S and R to signify what order the priorities go in. So we have, on the left-hand side, our priorities go 1 in the north position at the 12 o'clock position, 2 down here to the left, and then 3 further over to the right. So this is a counterclockwise rotation. Because we go counterclockwise with these priorities, this is called an S2-bromobutane. So counterclockwise is S. Now similarly with our mirror image over here, we've ranked our substituents, but this time we're going clockwise, and because we're going clockwise, that's an R. So in parentheses we have our S or R dash 2 dash bromobutane, and that's how you would name enantiomers. Now always when you're naming enantiomers, it helps to put the lowest priority group back. So when you're making models of this, you hold it by the lowest priority group and look at it face on. You can draw it out in the perspective formula with the hydrogen to the rear, and that does the same thing for you. When you have a Fisher projection, in order to name the enantiomers, you have to look at where the lowest priority is bonded. For example, when the lowest priority is bonded on the vertical, then clockwise is R and counterclockwise is S. So wherever you go from 1 to 2, ignore 4 and go to 3. 1 to 2, ignore 4, go to 3. That's only for a vertical bond. That follows the same rules as the perspective formula. Now, when your lowest priority is on the horizontal, however, it's backwards. So you might want to write those things down and keep them handy. Now, enantiomers are pretty cool molecules, and they will tend to bend light. Now, this is something that we will look into during Unit 4, I believe. Unit 4's lab. We're actually going to make a polarimeter. There's a section in your book, and I encourage you to read it, but the quick and dirty of a polarimeter is you have a light source, and it's typically a yellow light source, and in the laboratory it's dialed into a particular wavelength, and you have a polarizer lens. This polarizer lens will then orient the light in a particular manner. So then that light passes through a sample tube, and the plane of polarization may be changed and may not. If it is optically inactive, that means it does not bend light. Now there are some common household compounds that we'll look at in Lab 4 that do bend light. And what happens is after that light comes through the polarizer and you have your oriented light, when it starts to pass through the sample, it changes, it bends how it is. It bends the angle of the light coming out of the sample tube. So a chiral compound will rotate the plane of polarization of plane polarized light. If it rotates clockwise, it will have a plus in front of it, but if it rotates counterclockwise, it will have a minus. Now, there's no way to tell by naming the compound if it will be a plus or a minus. It can be named with an R and be plus or minus. It can be named with an S and be plus or minus. The only way to tell if it's a plus or a minus rotation in light is to put it through a polarimeter. Now remember that enantiomers are mirror images of one another, and they're identical in chemical formula. They're just mirror images, and because they are mirror images, one will rotate light in a positive direction and the other will rotate light in a negative direction. You can also have an enantiomeric excess. An enantiomeric excess tells you how much of one enantiomer is in abundance in a mixture. When you have an enantiomeric mixture that is 50% one enantiomer and 50% of the other, that's actually called a racemic mixture. 50% of each, that's what racemic means. But when you have an enantiomeric excess, you have this particular calculation. You might want to get familiar with it, but as promised at the beginning of the course, there's not going to be that much math for this course. Now, it is possible for compounds to have more than one asymmetric center, and those asymmetric centers would then be named differently. Now, each asymmetric center can produce two different isomers. Therefore, the maximum number of stereoisomers is 2 raised to the nth power. Now, n is the number of asymmetric centers. So when you have a compound like 3-chloro-2-butanol, you can expect there to be 2 squared, because there's 2 asymmetric centers, or 4 stereoisomers. Now, 1 and 2 will be enantiomers, and 3 and 4 will be enantiomers. Now, with these compounds, 1 and 2 are enantiomers, and 3 and 4 are enantiomers. But what is the relationship then between, say, 2 and 3, or 1 and 4? They're part of the same parent structure, really. So 1 and 4, 2 and 3, they're called diastereomers. Diastereomers are stereoisomers that are not enantiomers. So you can think of it as sets of twins. If 1 and 2 are twins, and 3 and 4 are twins, well, 1 and 3 and 1 and 4, they're still siblings, but they're not twins. 2 and 3 and 2 and 4, they're still siblings, but they're not twins. So diastereomers are like the sibling molecules, where enantiomers are the twins. Now, when you're identifying asymmetric centers, it's important to be able to pick out where your groups are and what they look like. When looking here at this carbon that has bromine attached to it, this group is the same as this group. Therefore, this is not an asymmetric center, because what you have is two groups that are the same attached here. It's kind of like saying this. You might as well be saying this. You have two groups that are the same, and therefore it is not an asymmetric center. Now, we talked about diastereomers and enantiomers. We also have what is called a meso compound. Now, a meso compound has a superimposable mirror image, and that superimposable mirror image is here. Now, they are optically inactive even though they have asymmetric centers. So here we have an asymmetric center, and here we have an asymmetric center, but the mirror image is superimposable. Now, you can also see that this compound has a line of symmetry. If it has a line of symmetry, it is optically inactive. Now, just as a rule of thumb that you might want to keep around on a cheat sheet or something, a compound that's going to have two asymmetric centers, look in here, that has the same 4 groups bonded to each asymmetric center. So we have hydrogen here, we have our alcohol group there, and we have our methyl groups. So we have a line of symmetry here. Now, this is a meso compound. It has a line of symmetry, but we have these 2 asymmetric centers. Now, these 2 asymmetric centers can flip these compounds in order to form enantiomers. So a compound that's going to have 2 asymmetric centers that have the same 4 groups bonded to each asymmetric center is going to have a total of 3 stereoisomers. 1, 2, 3. It just happens that 2 and 3 are twins, and your meso compound is the older sibling. Naming stereoisomers still means you need to assign priorities to your groups with the same rules. The ligand with the highest atomic number has the highest priority, therefore hydrogen is going to have the lowest priority. And then you go in order. You have 2 carbons, so that's a tie. The carbon that's only attached to a hydrogen here, this carbon is attached to a bromine and another carbon. So it's going to be the second priority. So we're going to go this way. This is counterclockwise. So this asymmetric center is an S. This asymmetric center over here, again, assign your priorities, see how it rotates, and this is an R. So in order to name this, we have assigned S and R to our asymmetric centers, and we need to find our longest chain. We have a 4-carbon chain, which means I have a bute, and I have this alcohol group, which means I have an OL at the end. This is on carbon 2. If this is 1, this is 2, here's 3 and 4. The alcohol has priority, so that's going to be 2-butanol, so let's name the rest. On carbon 3, we have a bromo. So to identify which one is S and which one is R, we're going to use the same numeric identifier for our carbons that we would use for any other substituent, and call it 2S, 3R, and that's in parentheses, dash 3-bromo 2-2-butanol. You can name stereoisomers the same way with the Fisher projection. Remember, when you have your lowest priority group on the horizontal, when your priority groups rotate clockwise, you're looking at naming it an S. Remember, on the horizontal, it goes in the opposite way as the perspective formula. So this is number 2 carbon, and this is number 3 carbon. What they've shown here with the red numbers is the priority. So we still have 2S, 3R, 3-bromo, 2-butanol.